Okay, it is my pleasure to introduce Jihun Park from IVS CGP Posttech, who's going to speak about Cayley octads, plain quartic curves del Pezzo surface of degree 2, and double Veronese cones.
Okay, so thank you for introduction and invitation. So today I will talk about Cayley octads and plain quartic curves and their features, surfaces of degree 2 and double Veronese cones. So we have 4 keywords for this talk. So I have a following 4 objects. So to explain, so the first one is the zero-dimensional object, which regular Cayley octads, which will be defined later. And I have a one-dimensional object, which is smooth plane quartic curves. And I have two-dimensional object, which is a smooth feature surface of degree 2. And finally, I have three-dimensional object, which is a 28 nodal double Veronese cones. So today, we'll consider their relations. I mean, the relations among these 4 objects. So in this diagram, so I have top of the diagram, I have smooth plane quartic curves here. And I also have the feature surface of degree, surfaces of degree 2. Left-hand side and right-hand side, I have a 28 nodal double Veronese cones. And in the middle, we have regular Cayley octads. So we know when you have the smooth plane quartic curves, we can always define the smooth feature surface of degree 2. I mean, there is a one-to-one correspondence between these 2 objects. And today we'll construct the one-to-one correspondence between this smooth plane quartic curves and the 28 nodal double Veronese cones. So we can define the one-to-one correspondence between this three-dimensional object and this surfaces. Also, we have this regular Cayley octads in the middle, and this guy has the 36 to 1 correspondence to each of them. So I will explain one by one. All right, so let me first define the Cayley octads. So a Cayley octad is an unordered set of 8 points in P3 that consists of an intersection of 3 quadrics in P3. So it's just the 8 point, which consists of the intersection of 3 quadrics in P3. So for a given Cayley octad, pi, we have linear system of quadrics passing through all these 8 points of pi. And this linear system is known to be a net. It's a two-dimensional object. I mean, two-dimensional linear system. So this is a two-dimensional linear system. So we have 3 linearly independent quadric homogeneous polynomials, F0, F1, F2 over P3 that generate this two-dimensional linear system. So that means every element in this linear system is defined by quadric homogeneous equation in this form. So x times F0 y plus y times F1 plus z times F2 for some x, y, z. All right, so you have the quadric equation like this. And this can express, this can be expressed as the 4x4 symmetric matrix M over pi with the entries of linear forms in x, y, z. All right, so this is the quadric equation, and you have the value of x, y, z. So you have 4x4 symmetric matrix. All right, and then like this determinant of this metric defines a plain quartic curve h of pi in P2, right? Because this is a 4x4, so you have the determinant defines the degree 4 homogeneous equation. P2. So we have here this plane quartic curve. And this plane quartic curve is called the Hessian quartic of this net. So this quartic parameterizes the singular members in this linear system. I mean, this two-dimensional linear system of the quadrics in P3. All right. All right. So a Cayley octad, which consists of the 8 point of the intersection of 3 quadrics in P3. A Cayley octad is called the regular if this Hessian the quartic is smooth. All right. If this guy is smooth, this guy is smooth, then we say this Cayley octad is regular. All right, so this is the definition of regular Cayley octad. Okay, so let's move to a smooth plane quartic curves. So we consider a smooth curve C in projective plane P2 defined by a homogeneous polynomial f of degree 4. All right, and this is a smooth non-hyperelliptic curve of the genus 3. Right? Okay. All right, then this smooth plane quartic curve C has 28 bitangent. So, 28 bitangent lines. So, so line which tangent to the smooth plane quartic at two different points. 2 points. So there are ordinary bitangent line and there are special kind of bitangent line. Ordinary tangent line means it hits the, it intersects with the multiplicity 2 at 2 distinct points. Then we say this is the ordinary bitangent line. And the special case, so these 2 lines merged. So this line intersect this smooth plane quartic curve only at 1 point, but with the multiplicity 4. So we have 2 kinds bitangent line, and this T sub O is the number of the ordinary bitangent line, and this T sub H is the number of this special bitangent line. And the sum of these 2 numbers is 28. This is a classical result, right? All right, and we have, this guy, a plane quartic curve has the inflection points, and we also have the 2 special, 2 kinds the inflection points. One is the ordinary inflection point, and the other one is the hyperinflection point. Ordinary inflection point is the point with the multiplicity 3, and hyperinflection point is the inflection point with the multiplicity 4. So multiplicity 4 means this line hits the curve only at 1 point. Means this one is the tangent line at this hyperinflection point is the bitangent. The special kind. So number of this special, the hyperinflection points is the same as the number of this special kind, the bitangent lines. Okay, so, and we have this relation, 24. All right, and the dual curve of the smooth plane quartic curve is the plane curve of degree 12. And with the T0 nodes and the I0 simple cusp and TH singular point of type E6. Type E6 means it's like the singular point looks like this x to the cubed plus y to the fourth. Right? It's that kind of the singular point is called the type E6. All right, so We have this many nodes and this many simple cusp and this many E6 type singular points. And it's known that there are 36 inequivalent to symmetric linear determinant expression. Let me explain what this means. All right, this term goes back to the 1855, the Hesse, and the 1902 by Dixon. So what they proved is, so every smooth quartic curve can be expressed as the determinant of a symmetric matrix, a 4x4 symmetric matrix of their linear forms. And there are exactly 36 inequivalent to symmetric linear determinant matrix, which defines the same smooth plane quartic curve. So equivalent means the up to like coordinate changes. So it means the so we have up to this inequivalent. The equivalent. So we have the 6 different symmetric linear determinant expression. So a given smooth plane quartic curve C. So we can obtain the 36 distinct nets of the quadrics in P3 up to projective transformation. All right. So this is the net of quadrics. So you have this expression. This defines the net of quadrics. And this Aij is the 4x4 symmetric matrix, and Bij symmetric matrix, 4x4 symmetric matrix, and this Cij is the 4x4 symmetric matrix. So this is the generator of this net of quadrics, and then this is the expression. And this guy defines this quadric, and then we have 36 different type of this net of quadrics. Okay. All right, and we need some information of the theta characteristic. So let me define first the theta characteristic on the smooth curve C. A theta characteristic on a smooth curve C is a divisor class theta, such that the 2 times theta is hold on, sorry. Just seminar. Sorry. So let me define again. So a theta characteristic on a smooth curve C is the divisor class theta, such that the 2 times theta is the canonical divisor. And a theta characteristic theta is said to be even if H0 is even, and the is art if H0 is the art. Okay. So the number of the theta characteristics of smooth plane quartic is 64. Actually, there is 2 raised by 2 times the genus. So that's why you have the 64. And the number of the odd theta characteristic of smooth plane quartic is exactly 28. Actually, this 28 given by the bitangent. So bitangent intersect the 2 points, and this 2 points defines the odd theta characteristic on the smooth plane quartic. And the number of the even theta characteristics of smooth plane quartic is 36. This 36. So an even theta characteristic theta of smooth plane quartic curve C defines the embedding of the C into the P3 by this type of linear system. K canonical plus this theta. So you have this embedding, and the degree of this divisor is 6. So this space curve S has the degree 6. So a given regular Cayley octad pi defines the net of quadrics in P3. And this net of quadric produces a Hessian quartic curve h of pi in P2, which is smooth because we are assuming that our Cayley octad is the regular. Okay, and the singular points. I mean, the singular. So in this net, I mean, the two-dimensional linear system and this net of quadrics, there are singular quadrics, and this singular quadrics are parameterized by this Hessian quartic, and we track this singular point of each singular quadrics, and then this singular points survive out of a smooth curve S of pi of degree 6 in P3, which is called the Steinerian curve of the net. And it is known that there is an even theta characteristic, theta of pi, such that this linear system, I mean K plus H, I mean K plus the theta defines an isomorphism of the Hessian quartic onto this Steinerian curve. Okay, so we consider the set, this script n. That consists of the isomorphism classes of regular Cayley octad modulo projective transformations. Okay, so we consider all like a regular Cayley octads up to the projective transformation, and we consider the set script T that consists of the pair C and theta, where C is the smooth plane quartic considered up to isomorphism, and the theta is the even theta characteristic on C. And we define the map, this the capital theta from the script N to the script T by assigning for each Cayley octad. So you put here the Hessian quartic of this net, and there you put this even theta characteristic defined in the previous slide, related to this Steinerian curve. And this theorem says this map is the bijective. There is the one-to-one correspondence, and this theorem, I think, not sure, but it goes back to this Hesse and the Dixon. But for the contemporary proof, we better look at this Bobir's paper in the 1977. It provides the contemporary proof. All right, so this is so far I explained about mainly about the smooth plane quartic curves, and let's move to the smooth Delphi surface of degree 2. All right, so now we consider smooth Delphi surface of degree 2, which is smooth such that there is anti-canonical divergence and it has the anti-canonical degrees 2. So everybody knows every smooth Delphi surface of degree 2 can be obtained by blowing up P2 at 7 points in general position. In other words, no 3 of them lie on a single line and no 6 of them lie on a single conic. And on this surface, the anti-canonical linear system defines a double covering of P2 branched along a smooth quartic curve. And we know every smooth Delphi surface of degree 2 can be obtained by taking the double curve of P2 branched along a smooth quartic curve. And the four vex of this 28 bitangent lines to the branch quartic curve defines the 56 minus 1 curves on the double cover, because each pullback of each bitangent produce the 2 minus 1 curves upstairs, right? So we have this 2 times 28, which is the 56 minus 1 curves. And we always choose the 7 disjoint minus 1 curves out of this 56 minus 1 curves. And when you contract this minus 7 minus 1 curves, you get the P2 and the 7 point in general position. All right, so situation is like this. So we have a regular Cayley octad, the V, and this is 8 points. We choose the 1 point P, from this Cayley octad. All right, so here in P3 you have 8 points, right? And then you chose the 1 point P. And then you project the other 7 point to P2 from the P. Then you can check this 7 point in P2 will be in general position. And you blow up this P2 along this 7 points. Then you will get a smooth stereo feature surface of degree 2. And this, and taking this anti-canonical linear system, you get this double cover from this feature surface of degree 2 to P2. And this double cover branched along the Hessian quartic curve of this net given by this Cayley octad. I will explain why this feature surface, this double cover branched the Hessian quartic curve later. All right, so this projection, we had this regular Cayley octad in P3, and we obtained this 7 point in general position in P2 by project the 7 point from the 1 point. All right, and this procedure is turn out to be a Gale transformation. Gale transform, and by the Gopa duality, you can reconstruct given the 7 point in general position, you can reconstruct this regular Cayley octad, which gives this 7 point. All right, and let's go to the 3-dimensional object. All right, so a double Veronese cone is a 3-fold with the Gorenstein terminal singularities, and whose anti-canonical divisor is M4 and divisible by 2 in the Picard group, and it has anti-canonical degree 8. So in other words, this is the feature 3-fold of degree 1. All right, so let me explain how to construct this 28 nodal double Veronese cones from the regular Cayley octad. All right, so first let me explain the one lemma. So lemma says the 7 distinct points in P3 are from the regular Cayley octad. This is the this is 7 points from the regular Cayley octad, then if and only if the following 2 conditions must be satisfied. So first of all, a discrete arrow P1 up to P7 is the linear system of quadrics which pass through the 7 points in P3. So first condition says every element of this linear system is irreducible. And the second condition is the base locus of this linear system. Actually, this is a net and consists of the 8 distinct points. which is actually the this regular Cayley octad. So this two, statements, they are equivalent. So if this guy is the 7 points from the regular Cayley octad, and if and only if these two conditions must be satisfied. Okay. All right, and we have the another lemma here. So the previous two conditions, A and B, are equivalent to this three conditions. So in other words, this 7 distinct points in P3 comes from the a Cayley octad if and only if the following three conditions satisfy. All right, so the first condition says no points, no 4 points out of the 7 points are coplanar. Okay, so plane must contain the 3 points, no 4 points. In particular, no 3 are collinear. And all points P1 up to P7 are not contained in a single twisted cubic curve, the cubic curve. Okay, and the last condition says for each I, you consider this 6 point. You delete the PI out of this 7 point, then you have this 6 points. Then this 6 points determines the unique twisted cubic curve. The twisted cubic curve is passing through this 6 point. And you consider also their line passing through the point PI and the one of points in this 6 points. Then condition says this twisted cubic curve and this line meet neither twice nor tangentially. Okay, so these 7 points out of the 7 points comes from the regular Cayley octad if and only if these three conditions satisfied. Okay. All right. Then let's construct this 28 nodal double Veronese cones from this regular Cayley octad. All right, so we have this regular Cayley octad, and you choose 1 point P from this regular Cayley octad. All right, and we denote the remaining 7 points by P1 up to P7. All right, and each PI and PJ, PI, PJ determines the line Lij in P3, and this 6 point, you remove this point P, chosen point P, and the PI. Then you have the 6 points, right? And this 6 point uniquely determine a twisted cubic curve. Let's say this is a CI, all right? Then we have 21 such lines, right? You have, you see you choose the 2 out of 7, which is the 21 possibilities, right? So you have 21 points, and you have 7 choice of the PI. So we have 7 such twisted cubics. So 21 plus 7, so we have 28 curves here. All right. Now we blow up P3 at this 7 points. And we have P3 hat here. That's the blow of P3 at this 7 points. All right. Then the anti-canonical divisor upstairs, the P3 hat is the NAPMV with this anti-canonical degree 8. All right, and let's say this Lij tilde is the proper transform of the line and this line, and Ci tilde is the proper transform of this twist cubic. And this proper transforms intersect the anti-canonical divisor trivially. And so normal bundles is O minus 1 plus O minus 1. Okay. All right, so this is the statement originally from the Prokhorov, and we like somehow like polished this proposition. I mean, they improved this proposition. So this is the blow up we considered in the previous slide. So P3 blow up at this 7 point. Okay. The 7 point comes from the regular Cayley octad. Okay. All right, and this map, this pi, I mean this phi given by this linear system minus 2k. All right, then the proposition says that this map is the bidirectional morphism, first of all. And the exceptional divisor, I mean exceptional locus of this is the actually the disjoint union of this 28 curves. I mean the Lij tilde and Ci tilde. That's the exceptional locus of the pi phi. And this variety V is the 28 nodal double barrel cone. That's the proposition. And the what Prokhorov proved is the following. So every double barrel cone with the 28 singular points can be obtained in this way. In this way means the you choose the 7 point from the actually what Prokhorov proved is the following. So you have the 7 points satisfy this 3 conditions. 3 conditions. Then this blow up satisfy this condition. So every double barrel cone with the 28 singular points can be obtained in this way always. All right. So far I explained how we can construct the 28 nodal double barrel cones from the regular Cayley octads. All right. And now I want to explain how to construct the 28 nodal double barrel cones from the smooth plane quartic curves. All right, so we start with a smooth quartic curve C in projective plane P2 given by this equation. This is our the homogeneous equation of degree 4. All right, and we consider the dual projective plane P check, and this STU. And this point is the general point in this dual projective plane. All right, then this general point correspond to the general line in P2 given by this equation. All right, and this general line in P2 they intersect our quartic 4 distinct points, x1, x2, x3, x4, lying on this because I'm assuming that this line is the general. All right, then we may regard these 4 points as a points on the affine line. All right, so on C you have 4 distinct points. Then so we could define the cross ratio like this. All right, this has the 6 different values according to the order of this 4 points. I mean the x1, x2, order of the x1, x2, x3, x4. All right, but the J function is the invariant with respect to the reordering of these 4 points. So this lambda is the cross ratio, and our J function defined by this this function. I mean this way, and this is the invariant with respect to the ordering. All right, and you see this is the symmetric polynomial. I mean the rational functions with respect to x1, x2, x3, x4. All right, this is our quartic equation. So we replace here this z by this right? Because we consider on this our general line, and we have this equation will be a equation in terms of the x and y, and this bi is the homogeneous polynomial in STU. Okay. All right. Then we have the following identities for the elementary symmetric functions of this 4 variables. I mean the 4 numbers. All right. So each symmetric elementary symmetric functions can be expressed as the BIs, rational functions of the BIs. So as I said, this J function defined in here, and this is the symmetric. The denominator and numerator are all symmetric functions, polynomials in x1, x2, x3, x4, and we have the elementary symmetric functions in terms of the BIs. That means we can consider this J function as the rational functions in V0 up to V4. So indeed, we have this expression. Okay, so we express the original J function in terms of the B0 up to B4 here. All right, and this BIs is the polynomials in the STU. So, and using some computer aid, you can see this H2, H3 can be expressed in this way. All right, so and then like you replace the H2, H3 by the G4 times U to the 4th and U to the 6th, G6, then you will get this function. This is our J function in terms of the STU. Okay. All right, so this is actually the J invariant of the elliptic curve. So and the G4, this is the degree 4 equation, and this describes the points corresponding to the lines that intersect the line that intersect the C. I mean so each point, I mean on this degree 4 curve, so you have the point, and in this dual you have the line, and this line hit the C 4 distinct point, and you consider double cover of this line, the branch at this 4 points, then you get the elliptic curve, and the J invariant of this elliptic curve is the 0. Okay, and this G6, and this is a degree 6 points. Degree 6, I mean degree 6 curve, and each point corresponds to a line, and on this line you have 4 points, and this defines the elliptic curve whose J invariant is the 1728, the special kind, and this is the our J function. All right, so we have the starting from the smooth quartic, we obtain this quartic curve and this sextic curve, and then using this equation, we can define this hypersurface V of degree 6 in this weighted project space, and this is the double Veronese cone. Okay. So this Veronese cone has the 28 nodes, and each point, I mean, this 28 nodes comes from the 28 bitangents of the given smooth plane quartic curve C. And the V has the rational elliptic vibration structure of the P2 check. And this 28 points and nodes, this nodal points lie of the ordinary double points and the E6 type singular points of the dual curve of the C. So this is the way to construct the 28 nodal double Veronese cones from the smooth plane quartic curves. So in this way, you can construct the smooth one-to-one correspondence between smooth plane quartic curves and the 28 nodal double Veronese cones. All right, let me give you this some kind of like a summarization. Summaries. All right, so this pi is the blow of P3 at 7 distant points. These 7 points, which comes from the regular Cayley octad. Okay, and this is the small resolution of the singular point of the threefold V. All right, so this map is the contraction of our 28 curves. So 21 comes from the line which passes through the 2 points of the among the 7 points, and the 7 point comes from the twisted cubic which passes through the 6 points out of this 7 points. So this guy contract the proper transform of this 28 curves to here to the 28 nodal points, and this. And this is given by half anti-canonical linear systems of V. Okay. Actually, the quadrics from here. And this is the projection. So you have these 7 points, right? And we said this guy is from the regular Cayley octad. So you have the extra 8th point. So from this point, you project this 7 point. This is the projection. And this case is the coincide with the Cayley transform. And you have this 7 points. You have this 7 point, and you blow up this 7 point, and you get the reflected surface of degree 2, right? And you have the anti-canonical linear system here. And this anti-canonical linear system gives us the 2-to-1 map to the P2. And this ramification locus comes from the branching locus is the quartic, which is the Hessian quartic of this Cayley octad, which determined by the 7 points. So here you consider like line here in P2. All right, then pull back of the line here, you will get the elliptic curve here. And this elliptic curve comes from the one-dimensional sublinear system of our net of quadrics. And this one-dimensional, the pencil determines the 2 quadrics, and their intersection is the degree 4 curve in P3, which is the elliptic curve. If it's just smooth. So when you project this curve, this degree 4 curve in P3 project to the P2, using this rod, and you get the smooth cubic curve here. Right? So this linear system, the one-dimensional linear system corresponds to this line here, and so here linear system, the one-dimensional linear system and sublinear system correspond to your line. So when you get the here singular intersection of the 2 quadrics, then you will get the corresponding line has the singular fallback. So that's why the branching locus of this double curve is exactly the Hessian quartic of our net. All right, so let's consider this a diagram. This is from here. All right, so here we choose the 7 point out of the Cayley octave, the regular Cayley octave. We blow up P3 along the 7 point. We got this P3 hat, and then we construct the 28 curves to the nodal curve, and then we obtain this 28 nodal double Veronese cones. And this half anti-canonical linear system gives us rational elliptic vibration structure here. And this map is given by our net of quadrics. But this diagram is not unique. I mean, you have this. I mean, you have the fixed V, but you may have different P3 hat because of this. So at the beginning we have there is a one-to-one correspondence between the regular Cayley octaves and the pair. I mean the smooth plane quartic curve and the even zeta characteristic. So you have the 38 different non-equivalent this regular Cayley octave, which has the same Hessian curve. So you choose 7 point from here. You choose the 7 point from here, and then you blow up P3 along the 7 point, along the 7 point. So you get the P13 hat from here, and you obtain the P23 hat. And this, they are different. But when you contract this 28 points, I mean 28 curves, then you get the same V. And this weak fauna, these two weak fauna linked by a plus. And then one can show that this Cayley octave and this Cayley octave can be transformed by Kremer transform in P3. So to count how many diagrams like this we have, so we consider this orthogonal system. So a set of the 7 distinct odd zeta characteristics, zeta 1 up to zeta 7 on smooth plane quartic curve C is called the orthogonal system if satisfy the condition that this expression is an even zeta characteristic for each choice of the 3 distinct indices I, J, K. So when you have this orthogonal system, so the choice of the 3 distinct indices is you choose 3 out of 7, which is the 35. All right. So the orthogonal system can express the all even zeta characteristic except 1. So I said like this smooth plane quartic curve has always the 36 the even zeta characteristic. So when you have the orthogonal system, then you can express the 35 the even zeta characteristic in this way. So 1 is missing, right? So choice of the point in a given Cayley octave. So when you blow up the P3 to obtain this double Veronese cone, so we blow up the 7 distinct points, and this 7 distinct points comes from a regular Cayley octave, right? So you have from the regular Cayley octave, you have 8 choices. I mean, you have to delete the 1 point, right? So you from the 8, you have the 8 choices. So a choice of the point in a given Cayley and regular Cayley octad is choice of the orthogonal system. And this diagram is given by a choice of the orthogonal system up to automorphisms, preserving the sum of the odd set of characteristics in the orthogonal system. So in general, so you have the 36 different Cayley octad, which shares this smooth plane quartic curve as the Hessian quartic. And you have choice of the points, 1 point, which is 8. So in general, you have the 288 different diagrams. Okay, so this is it. Let me stop here. Thank you.
Okay, thank you. Are there any questions? You can either unmute yourselves and ask directly, or you can write in the chat if you prefer me to ask on your behalf. I do have a question from Arman Brumer, who's asking if the slides will be available at some point. So it's up to Jihun. If he wants to give them to us, we can put them on the website.
Can you think? I cannot see the. Wait. I don't. Can you see my screen?
I can see your screen, yeah.
I mean, wait. What was your question again? Can I see the?
No, I'm just saying. And Arman Brumer asked whether the slides will be available, and I say it's up to you. If you want, we can make them available on the website.
If you wish, I can provide. Yeah.
I do have a question. Could you go back to slide 2?
Slide 2.
It's the one with the graph of 1-to-1, 36-to-1 correspondences.
Okay. You mean here?
Yeah. So I guess my question is, suppose you have a plane quartic curve with A1 singularities or A2 singularities.
Singularities.
How much of this construction extends? I mean, even if you cannot say anything about the singularities, say of the double Veronese cones, do you get a double Veronese cone?
I doubt it. So yeah. Well, it's gonna be a bad singularities. Do you still get?
Sure. Because you still get a fun variety
because you're not gonna have the 28 singular points, first of all.
Yeah, sure, but you still get like a del Pezzo variety of degree degree.
But you will have the I think strictly less than the 28 singular points, right? And it's gonna be worse than the node, okay?
Sure.
But moreover, I mean, in some, I thought about it, and then I believe like it may even like be a one-dimensional like a singular locus.
But it's still a double Veronese cone.
Yeah, but it's not gonna be a Gorenstein.
Okay, that's I
mean it's terminal Gorenstein, then must be I think it's isolated, but it's not.
Okay, I see. Okay.
I have small question.
Sure, go ahead.
Hi, Jihun. So, question is that, for example, for del Pezzo of degree threefold, del Pezzo threefold of degree 2, we have clear picture when it's rational and when it's not. Yeah, depending on the number of double points. For example, for V1, for double Veronese cone, do you have some at least expectation when it's rational, depending on the position and the number of the singular of the nodes? For 28, it's rational. But,
it's rational, yeah.
Yeah, but for smaller number, at some point, it stops being rational. Do you have some expectation? Because for degree 2, for double cover of P3 ramified on QUARTIC, it's picture at least, it's clear. So you should have up to 10 singular points, and it should be factorial. With one, yeah.
Well, not sure in this case. I mean, our construction is. I mean, in this construction, I mean, construction like based on this non-factorial properties. So and this guy is always non-factorial. So if you reduce the numbers, I'm not sure, but it should be a small number.
Okay, thanks. We have a question from, not sure if I'm going to pronounce this right, Cecilia Salgado, which says, can you say something more about the rational elliptic vibration V2P2? What are the singular fibers, etc.?
I mean, the slide. And this?
I guess I didn't ask the question, but yeah, I think so, yeah. So you say V has a rational elliptic vibration structure over P2 dual. Can you say something about it? Say, for instance, what the singular fibers can look like?
Singular fibers. Wait. I mean, all singular fibers. I mean, the fibers are.
We have a guess on the chat. Are all irreducible nodal?
Yeah, nodal, like cuspidal, but I think it's always nodal.
Okay.
Not sure, but but I mean, it's sure that every fiber, I mean, the elliptic fiber is always the irreducible. So I bet it's going to be a node always, nodal elliptic curve. I mean the cubic. I mean this degree 4 in P3. So as I said, every curve, I mean every fiber comes from the intersection of the two quadrics in P3.
Okay, thank you. So if this is all, I think we can maybe leave it here. Thank you very much. It's been a very beautiful, classical looking talk. I love this thing. Yeah.
All right, thank you very much.
So, next week,
Thanks.
Rui Dervan from Cambridge. Thank you. Bye.